A 500-ton reactor lowered with 40 millimeters of clearance. A 1,000-ton tunnel boring machine driving a 770-meter shaft almost straight up the mountain. Transmission towers 380 meters tall, taller than the Eiffel Tower. The world runs on power systems most people never see being built. Here is how the largest of them get put together, from foundation to live grid. On the Inn River in Bavaria, Germany, a power plant that ran 100 years is being replaced, and the work begins with drilling rigs cutting board piles 70 meters into bedrock. The togging excavation uses every technique in the specialty foundation toolkit: board piles, diaphragm walls, ground anchors, jet grouting, backed by heavy dewatering to keep the 30-meter pit open. A 100,000 cubic meter excavation beside the power plant, secured by 420 board piles, each running 70 meters deep. That is the first half of Germany's largest hydropower renewal project, valued at 250 million euros. The pit cuts 30 meters into the earth, with the 420 board piles reaching even deeper, some down to 70 meters. Excavated material doesn't leave the site. It stays on for embankment backfill around the inlet zone. 20 kilometers upstream at Jettenbach, a new weir takes shape on the Inn Canal. Precast crane runway beams weighing tons each are lifted into position across the weir bays. Dam tables, modular steel barriers, are set into each bay so the field can be drained for installation and future inspections without halting the canal entirely. Back at togging, the base slab goes in. 2 meters thick across the powerhouse floor, it absorbs 340 tons of reinforcement steel and 2,000 cubic meters of concrete, poured to a precise slope ready for the 3 future pressure pipelines that will feed the turbines. Timber suction tube formwork sets the curved water passages below the turbines. Then steel suction tube armor is set by heavy load crane and concreted around to lock the geometry. With the pit dug and the base slab cured, the heavy machinery begins to arrive at togging. A 185-ton rotor, a 110-ton stator, 3 transformers in the forecourt, every piece tested to millimeter tolerance before the next can drop into place. The new powerhouse rises beside a protected 1924 building. Construction runs day and night through heat, cold, fog, and sun for 4 full years. Suction tube formwork goes in first. 16 timber pieces assembled into a single curved void below each turbine, encased in concrete. A heavy load crane lowers the 13-ton suction tube armor into the ring. The gap fills with concrete. A 30-ton stay vane ring follows for turbine 2, transferring pressure loads to the concrete. Roof beams, 17 meters long and up to 20 tons each, drop into place. 40-ton fish belly girders form the intake protection grid. The runner for turbine 3 lifts in. A 6-meter, 28-ton shaft attaches the same day, and the turbine cover seals it 4 days later. The 110-ton stator drops into the pit. 8 days later, the 185-ton rotor follows, spinning at 167 revolutions per minute. 3 Kaplan turbines deliver 118 megawatts total, nearly 200,000 households served, 25% above the historic plant. A 4-meter Kaplan runner travels by heavy truck, gets cabled to a crane, and lowers vertically into a concrete shaft that has waited years for it. Machine sets at the Mur plant go in over August and September. Kaplan turbines 4 meters across, with generators stacked vertically directly above each runner. After the turbines, the river itself gets moved. The temporary diversion dam goes down, and the Mur flows through the new weir for the first time. The transformer powering up the new Mur plant has run for 2 decades already, pulled from a sister hydropower station and rebuilt to current standards. A heavy mobile crane lifts the unit over the substation wall, lowers it onto rollers, and crews ease it along rails to its final position. Lift a 95-ton Kaplan runner into a turbine pit with 3.9 millimeters of clearance. That test runs every revitalization. The 7.8-meter runner at Walsee Midderkerken drops in by crane, watched down to the millimeter. Pumped storage demands the same precision at a heavier class. The rotor at Limburg 3 weighs 355 tons, lowered by a twin-hook ceiling crane rated 350 tons per hook into the stator below. Conventional hydropower fills the grid on demand. Pumped storage does something stranger. It absorbs excess wind and solar at midnight, pumps water uphill into a mountain reservoir, then releases it at peak hour to generate electricity. The biggest of these sit hidden inside the Alps. Rysek 2 in Carinthia connects 2 existing reservoir systems, Malta and Rysek, through tunnels cut entirely inside the mountain. A cavern 80 meters long, 25 meters wide, and 40 meters tall was blasted out of solid rock to house 2 reversible pump turbines totaling 430 megawatts of installed capacity, with no new surface reservoir required anywhere. Limburg 3 is built to absorb Europe's surplus wind and solar in seconds. 2 dams over 100 meters tall hold back more than 160 million cubic meters of water. The release runs 480 megawatts. The pressure shaft is a feat, 770 meters long, 5.80 meter bore diameter, climbing a gradient over 90%. A custom 105-meter, 1,000-ton boring machine cut it in 4 months. 3 bracing levels kept the machine from sliding down the slope at any operating state. The cavern reaches 62 meters long, 25 wide, 43 tall, 51,829 cubic meters of rock blasted out using 64 tons of explosives. Building a 480-megawatt machine inside a mountain is one job. Hand stacking 90,000 dynamo plates, each 0.5 millimeters thick, to build the stator that converts water pressure into electricity is another. Fitters begin layering the stator and rotor of Machine 1. The laminated structure aligns magnetic fields for higher efficiency. The rotor needs 6,500 layers around the central shaft, nearly 3 months of work, with the steel pack heated repeatedly to 160 degrees and pressed before being shrink-fitted onto the shaft. Inside the pressure shaft, workers grind weld seams between pipe segments while standing on a 90% gradient. Above ground, the high mountain reservoirs are drained in February 2024 to allow intake structure construction. Just 30 meters of rock separates the inlet from the connecting tunnel. Engineers drill roughly 150 boreholes and blast through 2 meters of it in one shot. Copper bus bars get wrapped in glass silk tape and cured with resin, 4,320 windings in total. Mid-May, the gas-insulated power export line gets coupled. In July, the 130-ton, 4.90-meter-wide ball valve is lifted into level 0, a giant water tap regulating flow to machine 1. By September, the 370-ton rotor lowers slowly into the stator at millimeter precision. 4 months from commissioning, the last components slot into Limburg 3. A 200-ton transformer crawls in at walking pace. The third runner lowers into Spiral 1 at 338 centimeters diameter. Mean head between the reservoirs is 365 meters. Test rounds confirmed the rotor turns. Ball valve and converters stand ready. Storing energy inside a mountain takes years of tunneling. Building a nuclear power station demands a different kind of scale. At Hinkley Point C, thousands of workers operate across day and night shifts, keeping construction moving around the clock. The roof of Unit 2 is in place. Cooling water tunnels are complete, and work has shifted indoors, where crews install the pipework, valves, supports, and cabling required for the plant. Inside Unit 1, key nuclear systems are taking shape. 4 520-ton steam generators are installed and connected into the primary circuit, while the pressurizer is already in place. The turbine hall now contains the Arabelle rotor. Before completion, both units still require 700 kilometers of pipework and 10,500 kilometers of cabling. The reactor pressure vessel is the centerpiece of a nuclear power station, and placing it leaves almost no margin for error. Unit 2's reactor pressure vessel, a 500-ton steel cylinder, was lifted by Big Carl, currently the world's largest crane, and carried to the reactor building. Inside, an internal polar crane lowered it into the reactor pit with 40 millimeters of clearance on either side. Unit 2 is progressing 20 to 30% faster than Unit 1, the result of applying lessons from the first build. When both reactors are operational, the station will supply low-carbon electricity to 6 million homes. The turbine hall holds equipment as complex as the reactor itself, and replacing a failed component is its own major operation. A generator rotor replacement begins with an overhead crane lifting the damaged rotor from the generator housing. While the stator interior is inspected, a spare rotor is positioned and aligned along the shaft axis. It is then lowered into place with high precision before final shaft connectors and fastening work are completed. The most demanding lifts in nuclear construction combine extreme weight with extreme precision simultaneously. At the Eider site in France, vacuum vessel Sector Module 6, 1,330 tons, was removed from the assembly pit for repair. Dozens of sensors and cameras tracked the load continuously. Lifting clear took 3 hours. The module was then rotated 45 degrees with 20 centimeters of vertical clearance, aligned to millimeter accuracy, and lowered into a 22-meter bracing tool for disassembly. While nuclear stations concentrate power at a single site, renewable energy scales through repetition across land. Austria's largest photovoltaic project covers more than 130,000 square meters with over 35,000 modules. Installation reaches 1,000 panels per day at peak pace. Electricity from the site feeds directly into a neighboring industrial facility for on-site use. A utility-scale solar park follows a fixed construction sequence, each phase complete before the next begins. Steel foundation posts are driven into the ground, establishing the structural grid. Workers mount aluminum support rails across the posts to form racking. Excavators cut cable trenches between rows. A prefabricated inverter station arrives by heavy transport and is craned into a concrete foundation pit. With electrical infrastructure in place, thousands of panels mount onto the racking and inverters fit below the arrays. Wiring teams connect outputs, measure voltage, and configure each inverter before testing. The finished Erlenbach Park covers 3.4 hectares and produces 1.9 megawatts. A wind turbine requires a foundation, a tower, a nacelle, and 3 blades, and each involves a separate heavy construction sequence before the machine can turn. Access roads are built first, compacted to carry the oversized transport vehicles delivering tower sections and blades. The foundation excavation produces a circular pit at the turbine center. A dense steel reinforcing cage is assembled by hand before concrete is pumped in, with the anchor bolt ring cast precisely into the pour. Tower sections arrive by low loader, each a steel cylinder craned vertically onto the section below. The nacelle, housing the generator, gearbox, and main shaft, is lifted onto the tower top and bolted into position by technicians working at height. The 3 blades are assembled at ground level onto the hub as a single unit. 2 cranes then lift the complete rotor assembly together, rotating it from horizontal to vertical during the lift before connecting it to the nacelle shaft. The Enercon E33, producing 330 kilowatts, represents the smaller end of modern turbine capacity. The construction sequence for any turbine, regardless of size, follows the same logic from the ground up. Pipelines carry the molecules that make electricity possible in the first place. 1,224 kilometers of welded steel pipe running across the bottom of an entire sea. 2 parallel pipelines cross the Baltic seabed, linking natural gas supplies with major energy markets. Construction required 202,000 large-diameter steel pipes, each 12 meters long, and later coated with concrete to reach 24 tons. More than 30 vessels supported logistics, while environmental monitoring included around 1,000 sampling stations. Pipe sections were welded, tested, and lowered to the seabed before final connection. Together, the pipelines transport 55 billion cubic meters of natural gas annually. A pipeline crossing an entire sea survives only if every weld, coating, and valve performs exactly as designed. The system uses high-strength steel pipes manufactured in multiple countries and coated with heavy concrete to withstand Baltic seabed conditions. On the pipe-lay vessel, each pipe section is welded, inspected by ultrasonic testing, protected with anti-corrosion sleeves, and sealed before installation. Along shallow sections, the world's largest seabed plow cuts trenches so the pipeline can settle securely below the seafloor. At the landfall terminal, custom-built 48-inch high-pressure valves regulate gas flow. Quality control follows every stage. Solar and wind generate electricity for domestic grids. Liquefied natural gas moves energy across oceans in a different form, and building the infrastructure to produce it is unlike any other construction project. At Kitimat, processing facilities spread across a coastal site surrounded by mountains and deep water. Steel structures, columns, and pipe racks extend across the complex. SPMT vehicles transport oversized modules at walking speed, while crews complete welding and assembly work at height. Safety briefings start every shift before work begins. Throughout the plant, vessels, columns, and modules wait in designated staging areas. Each component must be installed in sequence before a liquefaction train can operate and prepare natural gas for export. The liquefied natural gas storage tanks cannot be roofed with cranes. The roof arrives at the bottom and has to rise from inside. At Kitimat, a 1,540-ton, 92-meter roof was airlifted into position and welded in place atop the 56-meter tank. Above the tank farm, the process columns must be lifted to vertical, and the main absorber is the largest single piece of equipment on site. The 830-ton, 54-meter absorber was rotated upright by 3 cranes in a lift lasting 4 to 8 hours. The absorber changes the skyline. The final module closes the last open workfront, a different kind of milestone entirely. After 2 years of logistics linking fabrication yards in China and multiple contractors, the last major Train 1 module arrived on SPMT vehicles, unlocking all remaining installation work across the train. Build a hydropower giant in the mountains or a pumped storage cavern under the Alps, and every megawatt is still trapped where it was made until something carries it to the city. The link between generation and consumption is the most fragile piece of the entire energy system, a steel tower with cables hanging in the air. On the Zhoushan archipelago in eastern Zhejiang, the world's tallest transmission towers carry power across an ocean shipping lane. 2 towers reach 380 meters, nearly 4 times the height of London's Big Ben, and taller than the Eiffel Tower in Paris. The towers sit on a route 39 kilometers long, linking Zhoushan City to Ningbo on the mainland. Of 85 towers total, 14 cross open sea, and the other 71 stand on land. 2 reach the full 380-meter height. The reason is shipping clearance. Zhoushan is one of the world's largest seafood processing ports, with cargo and fishing vessels passing constantly underneath. Lower towers would let conductors sag into ship paths. Total tower weight reaches 7,280 tons, also a global record. Conductors were strung using helicopters for the first time on a project this scale, since the islands and weather made conventional pulling techniques impractical across the open water spans. Stretch 1 transmission line, 2,121 kilometers across a continent, and the line itself becomes an energy backbone. The Beihaitan Zhejiang 800 kilovolt UHV direct current project sends clean power from the country's second largest hydropower station east. Roughly 60 billion kilowatt hours move annually across 2 UHV projects, displacing 27 million tons of coal. Ultra-high voltage is defined as 1,000 kilovolts or above for alternating current transmission, and 800 kilovolts or above for direct current transmission. In Gansu province alone, 4 such lines deliver more than 40 billion kilowatt hours of renewable electricity annually. A single helicopter inspection saves 3 million households from a power cut and finishes in hours what a tower climbing crew needs days to do. The catch: workers have to step onto live conductors carrying 500,000 volts in mid-air. Ultra-high voltage transmission technology covers 1,000 kilovolt AC and plus or minus 800 kilovolt DC and above. Compared to lower voltage systems, it carries more capacity over longer distances with less line loss and smaller land footprint, the whole reason west-to-east power transmission projects exist. Live-line helicopter maintenance is how damaged spacer bars get replaced without dropping the line. Linemen ride in a basket suspended 40 meters below the helicopter on insulating rope. The instant the basket contacts the conductor, a strong recoil kicks back. Workers have to predict and adjust posture immediately, or they cannot stand up at all. The shielding clothing is 75% Nomex and 25% stainless steel fiber, a wearable Faraday cage that diverts the electric field around the body. Helicopter live-line maintenance increases work efficiency 75% over traditional methods and cuts outage duration by at least 5 hours per defect. The 2 linemen and the helicopter crew communicate continuously, adjusting position in real time across narrow spacing between parallel lines. The cable lines that move electricity across continents need something even more solid than the towers, a concrete foundation that holds the tower against decades of wind, ice, and conductor tension. Pour one wrong and the whole line goes down. Each monolithic foundation for a 500 kilovolt river crossing tower takes 54 cubic meters of B30 F400 W8 concrete, poured continuously in 3 tiers, bottom, middle, top, over 20 to 24 hours without stopping, even through the night. Bolt 18.5 tons of steel angle into a 35.5 meter tower lying flat on the ground, and the bolts themselves become the weak point until anti-tamper nuts solve a problem most people never knew existed. Anchor Corner Tower U331 assembly begins with sorting steel angle bundles delivered to site and test-fitting nuts on every step bolt to verify thread quality. The lower body frame goes together flat, the bottom lattice plane first, then the upper plane raised with crane support. A pre-assembled side panel lifts in and bolts perpendicular into the main frame, giving the structure its 3-dimensional shape. Crossarms attach to the upper body. Heavy assembly bars and conical alignment pins force overlapping bolt holes into register before final tightening. Anti-tamper nuts get installed at every critical joint. When torqued to specification, the hex top shears off automatically, leaving a smooth dome below that no standard wrench can grip. Steel theft from rural transmission lines becomes physically impossible. At 88 meters tall and 152.6 tons, the second river crossing tower at the Lena gets built by tower crane reaching 95 meters up. An 11-meter, 2.9-ton crossarm lifts to the top and gets bolted on. The work platform follows. 2 towers stand symmetrically across the river, ready for 500 kilovolt conductor stringing. Open-air switchgear needs hectares of clearance. Pack the same 220 kilovolts into a sealed metal enclosure filled with insulating gas, and the entire substation shrinks into a single building. Gas-insulated switchgear, GIS reconstruction at a 220 kilovolt substation begins with site preparation under the production hall. Cells D03A, D03, D03B, D01A, D05A get assembled in sequence. Bus duct and transformer bushings dock in next. Control cables get routed around the equipment. Testing happens before energizing. The dust tolerance is absolute. Installation must stay clean of even airborne particles. Commissioning concludes on schedule, with full operation reached without delays. Sit on a live 500,000-volt conductor, like a bird on a wire, and the body stays safe because a Faraday cage suit equalizes potential the moment the metal pole touches the line. A hot suit of 75% Nomex and 25% stainless steel thread carries current around the body, not through it. Stringing conductors in summer and erecting towers in winter snow are 2 entirely different jobs for the same crews. And the tower steel itself comes off CNC drilling lines hundreds of kilometers before it reaches the field. Heavy hydraulic tensioners pull metal conductor along the line of towers. CNC plasma cutters drill steel angles for the towers themselves. Excavator and crane teams raise tower sections from horizontal to vertical in deep snow. Cross one transmission line over another and the schedule becomes the enemy. The lower line has to be switched off, dismantled, rebuilt, and re-energized in 6 days flat, while a brand new 500 kilovolt span gets strung above it. A reconstruction at the crossing of an active 220 kilovolt line with a new 500 kilovolt route runs to a 6-day shutdown. Day 1 begins with de-energizing the 220 kilovolt line, installing anchors and portable earth grounding. Days 1 to 2 cover removal of existing conductors and the optical fiber communication cable on the section to be rebuilt. Days 2 to 4 see conductor and jumper installation in the new 500 kilovolt span. Tension insulator strings get assembled, lifted onto the anchor corner tower, fitted with damping spacers, bird protection devices, and signal marker balls along the conductors. Day 3 restores the original 220 kilovolt span. Days 3 to 5 dismantle the temporary metal tower U220 N2.2+14 used during the work. Day 5 installs new conductors and jumpers on the 220 kilovolt line with hydraulic press crimping of tension clamps and assembly of insulator garlands on the new anchor corner tower. Day 6 completes the job and re-energizes the 220 kilovolt line.